Hey there, I'm back with another episode of Adventures in IoT. And this time we will be writing the firmware for an ESP32 C6 DevKit C1 board. And this mouthful is this board. We will be reading data from a sensor and sending it to an MQTT broker. You can find the links for the resources of this episode and links to previous episodes in this URL or this QR code. The ESP32 chipsets are very popular among the IoT community and also the do-it-yourself people. So we're going to take advantage of this one that is able to not only do the reading from the sensor, but it has the capability to communicate via Bluetooth, not interested in this case, via Wi-Fi, which is what we will be using, and also ZigBee and something else. In this case, we will be using Wi-Fi in order to talk to the MQTT broker, and we will use that Espressif has put in place to develop code for this board in Rust. Yep. So we will be using the standard development kit, which is the ESP IDF, and this kit allows us to write code not just bare metal without any operating system, but rather using an RTOS instance of the operating system. So our application will be running on top of that. We'll be benefiting from using the standard library in Rust, so having memory allocation, having threads, and so on. And we will be using those in this and the next episode. The ESP32 board that we're using in this episode has a neopixel in it. That is RGB LED. Actually, is a red LED, a green LED, and a blue LED that are controlled by a WS2812. And this WS2812 allows you to send signals and decodes these signals and assigns a different value to the red, green, and blue LEDs, allowing you to choose whichever color you wish. That is very powerful, and it can be used in many ways. We will be using it for the hello world, and we will be also using it for informing the user. What is more important here is that it requires some effort. You have to encode the signal in a way that the length of each of the pulses describes what the bit value is going to be. So that means that we could encode these signals manually, and that will be a little bit painful, but we can also use another feature of this board, that is having a remote controller transceiver. The remote controller transceiver was meant to encode and decode infrared remote signals. But in this case, the remote controller that is also known as MT, and I know that the initials don't match the name, this device can be repurposed to create signals of different shapes. We can use that, and we will be using a driver that uses that in order to talk to the neopixel. This driver is using an abstraction in order to talk to the RMT and to talk to the neopixel. But this abstraction comes from the effort of a workgroup in the Rust community that is called the Embedded Workgroup. The Embedded Workgroup has created a set of abstractions that describe common features in these MCU boards that we are using. However, among the things that are abstracted in this hardware abstraction layer, this is also known as the embedded hull, there is no description of an RMT. And so we wouldn't be able to use it, not even in version 1 that was released on January 9th, 2024. So a few days ago, when I started creating the code for this episode, this device wasn't included in the embedded hull version 1.0. The ESP IDF, the kit that we're using for writing Rust software for this board, is already implementing the embedded whole release candidate 1, and the one that is about to be released is adopting the final version, version 1.0. But in this case, the driver that we will be using will have to use the abstractions provided by the ESP rather than the ones defined by the workgroup. Those traits are not all we need to do the communication with the NeoPixel yet. Before we start with the setup for the tools that we need in order to be able to follow along, compile the code, and install it in the board, I would like to let you know that Expressive, which is the company behind ESP32, has put some effort in creating a Docker container with all the tools in it. So if you prefer to go this way, being by guest, it will be much easier. If you control Docker, you just run the container and it will do everything for you. In my case, I prefer to install these tools in my computer, and one of the requirements is that you have to have the bleeding edge version of the Rust toolchain. So we will install nightly in the computer and a few other tools together. If you have decided to install the tools in your computer, as I did, these are the instructions to do that in your macOS computer. If you're using a different kind of computer, if you're using a Windows or a Linux computer, then go to the written article for this episode, and I will have a link there to go to the instructions for installing the right tools for those platforms. In this case, what I'm going to do is to update the toolchain to have the nightly version of the toolchain and have the source code included so we can benefit from the latest developments in the standard library. In this case, I already have the latest version of the nightly toolchain, and so nothing is done. And here I'm going to use Homebrew in order to install CMake, Ninja, DFU, UT, and Python 3. So a building tool, templating tool, a tool to talk to MCU, and the Python language. Hopefully I also have the latest version installed for these things. No much problem here. And finally, I'm going to use some tools that will allow me to run them from Cargo. So there are extensions to Cargo, and we can use LD Proxy, which is a tool to forward linker arguments to the actual linker, ESP Flash, which allows us to flash the firmware into the ESP board that we're using, and Cargo Generate, which is a tool to create a new project from a template, in this case in GitHub. I'm not doing this one because I know that one of these tools, I don't have the latest version and it will take a long time to compile, but basically if you run this command and have some patience, you will get to the latest version of the tool. Let's use Cargo Generate to create our project from a template. So here we're using Cargo with the tool that we have installed, Cargo Generate, and ESP-RS is the GitHub user for Expressive's Rust code, and ESP-IDF-template is the template, the repository for the template that we want to use. And Cargo is just a parameter for that template. So here I'm running that, and it asks me what I want to call this project. And it's going to be Mosquitto -bzz. And it now asks me what I want it to be the target platform. And this is going to be meant for the ESP32 C6 that we saw before. So this is what I choose. And I have also the option to customize further the project, but I'm not going to do that. That's good enough for me. So let's go to the Mosquitto directory. And yes, we're going to run cargo B for cargo build. And let's wait for a second while it starts building that. And let me tell you that the first time you compile this, it's going to take a long while. a very long while. So I'm going to leave this running in the background here. And for you, this is going to be sped up, so it will look shorter. But no worries if the first time you run this takes a long time for you. After that, it won't be the case, okay? So finally, we have this project compiled, and now I would like to run it on our device. The binary has been created under target RISC v32 iMac ESP IDF. This is a debug version of the binary, and it has the name of the project, which is Mosquitto Biz. The dash monitor is meant to keep on reading the logs from the device while it is running the application. So we will be using this command, and I have the board connected to this computer, and it's asking me where I want to use, which is the device driver that I want to use to talk to this device. And well, it is now uploading the firmware to the board. And as you can see here, we get the information messages, and we have the Mosquitto bzz, hello world message printed here. So we're doing great. We could have got the same effect by running cargo R or cargo run. So let me show you that. Hopefully I have this here, and we do cargo R, and same thing happens. It doesn't compile anything now because it's already compiled. I send it to the same board. It is flash, and I get the same Mosquitto hello world message. From now on, we will be using this cargo run, and I'm going to show you what has been created in the project using Visual Studio Code browser, and then we will try to understand why cargo run does that, but that's the flashing to the device. Oh, this is the project that has been created with the template, and let's start going to the most obvious file, which is the cargo toml configuration. And here, as you can see, it defines some of the features that are available. So we're using the standard library, we're using Embassy, and the ESP services native. So this is the description. These are the dependencies. Basically, we have log to do the login, standard login, great for Rust, and we use ESP services, which is like the higher level abstraction for talking to the hardware and using the different parts of it. That's basically it. This mbuild, embuild is meant to do the compilation of the C++ code with all the CMake files. And the rest of it are just some dependencies that need to be there. We also have some profile settings that are not very relevant here, but which not for the code that we're going to write. And that's basically it. On top of this, we have build RS. The build RS is something that gets run during the cargo build process. And that is something that they have prepared, so it simplifies some of the things. You can do things on top of that. Actually, the Ferrio Systems people do checking for the configuration here, and that's perfectly fine. But we need this to be working properly. Then we have the Rust toolchain toml, which explicitly states that we're using the nightly version of the tool, and we are using the Rust dash source in order to be able to compile this latest version of the standard library. Finally, we have here the SDK config defaults, and this is the configuration for the ESP IDF. And here you can change, for example, the size of the stack of each of the threads or tasks, rather. And you can also do some other configurations. We are not going to touch this. This is the a free RTO or frequency, which is also something that people change, but we're not going to do that here. Inside of the .cargo, we have a config toml, and this is where some of the magic happens. Remember that before we were saying, why does it do the ESP flash thing when we run? Here, it chooses the target for the build thing. It also says what it has to be used for the builder. And here, the runner, it says, hey, when you want to run things, you need to use ESP flash with the flash command and then dash monitor option in order to be able to read the console writing. These are the default flags. So this is where we make our lives easier by having these defaults built in the cargo build and cargo run thing. Finally, I would like to show you what the content is for the main.s, and it is quite simple. It does this piece of code where it adds some patches, and that's something that we have to live with. And this is the initialization of the logger capabilities, the ones that we used in order to print to the console, the message that we were reading before. And using info from the login crate, from the login abstraction crate, we are able to print the hello world as we saw before. Now that we have the tools in place and we have created an instance of the project from the template, we are going to start writing the firmware. The goal is to have something similar to what we did in episode 2 that reads data from a sensor, and in this case, it will send it to an MQTT broker instead of using Bluetooth Low Energy. That means that we will have to connect to the Wi-Fi, and that we will be using then a connection to the MQTT broker with corresponding protocol in order to send the data there. Making the LED blink is considered the hello world of the embedded programming. We can take it a little bit further and use colors rather than just blinking. According to the documentation of this board, the ESP32C6 DevKit C1, the LED, the neopixel, is controlled by a GPIO pin. And we can have access to that pin using the peripheral singleton that is provided by the ESP that is the library that we're using in this case. So what we're going to do is do exactly that, get access to the peripheral singleton, and notice that it's complaining because, we haven't imported a symbol yet, but we do that, and no problem now. It's only complaining that we are not using the peripherals yet. So the next thing that we are going to do now that we have the peripherals is to use it in order to get access to the RMT. The RMT is the remote controller transceiver that I mentioned before, and that is the feature, the functionality of this board that we're going to use in order to encode the signal in the way that we need to tell the WS2812, the controller for the neopixel, this is the amount of red that we need, this is the amount of green that we need, this is the amount of blue that we need. The other thing that we need to have access to is the pin that is connected to the neopixel. And that, as I said before, is the GPIO. Now that I have created those accesses to the hardware features that we are going to use, we are going to add a driver that will use the RMT as needed and will send the data to the GPIO pin that we provide. That is a driver that is provided as a crate and that we are going to import here. So that is what we're doing now. We get the driver installed and we come back to the code and create an instance to this driver. So we create a neopixel variable. In this case, it's going to be mutable because we're going to write to it. And that neopixel driver uses a constructor that takes the RMT channel and the LED pin. With this neopixel in place, we can create a color instance and send it to the neopixel. Both the WS2812 ESP32 RMT driver and the extract for the color are provided by the library, so I will have to go and use the symbol here that is needed.
So let's go and do that. Let's go one by one and import the symbol. And here I'm also going to use this LED pixel color. And the only thing that I want to be sure here is that I'm also using the trait that can be used for defining the colors in all these different formats. Now that I have the symbols, let me show them to you. The symbols are here, okay? Now that I have these symbols imported, I can go and have this code here executed. Let's go and let's try that. And let's go to the terminal, cargo R to run it, and hopefully we will see a different color in the LED. It's compiling now. As you can see, it takes some time, but it's much shorter than it was before. And once we have compiled the driver, next time we don't have to worry about this compiling time because those crates are also going to be already compiled, so we don't have to do it again. So it does this, and the color of the LED has changed. Cool. But that is just changing the color from what it originally had to something different. Let's make it blink, but blink with different colors. So let's go back to the code, and I'm going to define a second color here. So this second color is going to be, in this case, red and blue, so purple. And we're going to use this color in a loop. So let me get rid of the printing that we had before, and we're going to have this loop that will do the same thing twice. We're going to use the neopixel to write the first color, and then we will swap to the second color and back again because this is an infinite loop. That would work, but we won't see the difference because we need some delay so our eyes are able to notice the difference. So let's go to this part of the loop and let's replace it with something that can have that delay so we can see what is happening. So in this case, we're doing basically the same. We're writing the first color, then waiting for some time. So let me have it here. So we're waiting for some time, and then writing the second color and then waiting again. This time is going to be 500 milliseconds, so half a second. And we just need to have these two symbols imported. So we're going to do that. We're going to import duration, and we're also going to import thread as a standard thread. Okay, so we can do this because this is using the standard library, and we have access to both things here. Now that we have this in place, let's go back to the terminal. Let's stop what we have and let's run it again. We are going to use cargo R again, and hopefully we will see the LED changing colors from yellow to purple and back to yellow. Let's see that. And yep, we have it there. So every half a second, we have yellow and then black. That's it. The next thing that we're going to do is to encapsulate the interaction with the LED in its own thread. We can do that because we're using expressive ESP32 library. That crate provides us with the ability to use the standard library, which means that there is an operating system behind the software that we're creating that provides us with memory allocation, with triggers, threads in this case. So we're going to benefit from those, and we will have the blinking thing in its own thread. We will need a way to share information between this thread and the rest of the system in order to know the state of the device and then inform the user accordingly. We are going to encapsulate the usage of the LED in its own thread. That thread needs to be aware of any changes on the status of the device, and use the current one to decide how to use the LED accordingly in order to inform the user. So first, we're going to need to define an enum with all the possible states. So here we create this enumeration. Sorry about that. And this enumeration has the OK status, the Wi-Fi error, and the MQTT error. We may change this later, but sounds reasonable for now. This is going to be one or the other. That's why it is an enum, the value of the status of the device. Now we can try to add an implementation for this enum that is going to be a drive from. So basically, we can create one of these values using a U8. So a number from 0 to 2. And in case something goes wrong, we will be returning an error. Otherwise, we will basically return the corresponding status. So 0 is everything is fine, 1 is Wi-Fi error, and 2 is an MQTT. We also would like to be able to convert the device status from one of these cases, one of the variants, to the UA, the corresponding UA representation. And we're going to do that by having this representation here. Let me get rid of this. Let's move this. And this representation is basically saying, hey, we can convert from the variant into the actual number, integer number, unsigned number for this variant. We're going to do something a little bit naive, that is creating a state here for the status. This is going to be a variable that we're going to share among the threads. And I'm saying this is naive. If you have ever done any Rust development before, you will immediately realize that this is not going to be a good idea. But just in case, we're going to do it here. So this is the status, and it is holding a device status as 8. So we're going to record it as a number. And we are going to make it mutable so it can be changed by one thread and used by the other. We also are going to define another structure that is going to hold the different steps of the blinking for the neopixel. So we're going to add this structure here that is going to be using 3 fields for the color, red, green, and blue, and a duration for this color. So with these 4 numbers, we're going to be able to say this is going to be, the first step is going to be red for half a second, then be green for another second, and whatever we want to use in order to inform the user of this status. Now that we have the color step, we can have an implementation for it. And this implementation is going to be a constructor. So it's easier for us to create a new color step by using just the number with the associated function. And for the device status that we had before, we are going to be able to have a sequence for the device status that is based on the information that it represents. So here, I'm going to define this new implementation that when provided with device status, it returns a vector of color steps. So it will have these sequences. So when it is okay, it will be basically green, then black for half a second. So it will be blinking slowly. When it is Wi-Fi error, it will be red and then off for 0.2 of a second, and then off for another 1/10 of a second. So it will blink longer in red and a little bit shorter while it's off. And for the MQTT error, it will use shorter periods for the light and longer for the pause, for the off moment, and it will be purple. That's it. That's what we're going to do in order to inform the user. With these things in place, we can now have a new function, which is the one that we're going to use to create the thread. Let's add it at the end of this code. So here, I'm going to create this new function that is going to be called report status, and it's going to take a peripheral that implements an RMT channel. This should bring some memories, and another one that is an output pin, maybe GP8. So here, what we're going to do is basically having the thing imported here. So we're going to import peripheral and also import RMT and hopefully the output pin. Now it is complaining because we are saying that this function never returns, and it's actually returning nothing, but it ends. So we will add a loop very soon now. But we have moved the creation of the neopixel from where we had it here into this function. So we are going to get rid of this part here, remove it, and we will be calling soon this function for spawning a thread. Now that we have this function created, let's add some additional things here. So we're going to keep the previous status and to avoid recalculating the sequence for lighting. So we're going to do that here. And we're going to keep the sequence itself. So we can reuse the sequence if the status hasn't changed. With these two things in place, what we are going to do is having the loop that we were missing. And the loop is going to do basically trying to get the status from the number that is stored in this share variable. And this status, if it is the same one as in the previous status, then, if it is not the same one as in the previous loop, it will record that one and update the sequence. Otherwise, it will do nothing. And after that, it will go through each of the steps of the sequence, light the LED accordingly, and wait for the amount of seconds, or milliseconds rather, of that step. The only thing that it is complaining here is that it is not able to compare these two values of the device status because we haven't added the derivation of the partial equality to the device status. And in order to assign it to, we also need to derive clone and copy. So let's do that. And that should be here. In the device status, we are going to derive clone, copy, and partial equality. And as you will see now, it is not complaining anymore. So now that we have this function, we can create the part of the code that spawns the thread for this thing. But before we do that, let me create the other thread. The other thread that we're using here is, let me try to be sure that everything is properly formatted. I'm going to add the second function here, which is the second thread that will be changing the status, in this case, every 10 seconds. So we are going to be updating the status, and we're not going to do something really fancy. It's just going from one status to the next, and the status changes every 10 seconds. Now that we have both functions, we're going to go and use them in order to spawn the thread. So we go back to the main function, and at the end of the function, where we have the initialization of the drive that we have removed, we're going to create the scope for the threads, and we are going to create a thread for each one of the two functions that we have there. Notice that it is complaining here, and this is one of the blessings of the borrow checker that Rust provides us with, that it tells us, hey, you are updating the status here, but you're using it here. That is a race condition, so bad idea. You shouldn't be doing that. So how can we do that? We can use several ways of doing that. We can use a channel and then updating the value only when needed. In this case, I decided to go with atomics. And instead of having a variable that is shared like that, we're going to replace this one with something that is an atomic value. So notice the difference here. It doesn't have to be mutable as we had before, but let me go and remove this line. And the only thing that we need to do is to create this atomic U8 where we are going to store the value. There are no atomics for enums, but we could do that with a mutex, but we're going to go very simple with this, and we're going to use the atomic U8. And obviously, I need to import the atomic U8 in order to be able to use it. Now that I have this atomic U8 there, I need to change the signature of the function that I was creating here. And instead of having the status as a U8, I'm going to replace that part of the content, and I'm going to make it slightly different. So we are just taking a reference to the atomic U8, and we are benefiting from the functions that an atomic provides us with, which is load and store. And here what I'm saying is memory ordering is not relevant because I'm only using one atomic. Here I would like to go and take this relax for ordering, and I'm going to do that here in the STD atomic. Here I'm going to use ordering and relax. And that should be it. Now, isn't it ordering? Here we go. It's not ordering atomic. Sorry. Much better now. Okay. Now we have the proper implementation for for reporting the status. We take the atomic and we read from the atomic. And we also need to change that for the change status. So we are going to do that by rewriting the whole function and using the atomic instead of the variable that we were using before. As you can see, the code is very similar. The main difference is that I take an atomic, a reference to the atomic as an argument, and I load it, and then we go out here and store it. Okay? Now we have to do the proper invocation in order to spawn the threads because we are not using the same arguments anymore. So we're going to replace these two here with the proper implementations here. And that should be it. Let's go and ergo run. And if I have done this properly, we should be able to watch the LED blinking in green initially. So status okay. Now it will switch to red, blinking fast. And then with a shorter period for the purple, but a longer pause, it will be purple. Yes, and it works.
It is time to start reading from our temperature sensor. Just kidding. No more temperature measurements in this episode or any other from now on in this series. But now we are going to use this OSEPP Sound01 sensor. This is one of the available sensors in the market. You can use any other if you wish. Some of them have a digital output. This one has 3 pins here. The 2 are for voltage and ground, and the other one provides us with an analog measurement of the sound. We're going to use the analog to digital converter that is included in our device in order to transform the analog voltage that comes here into some value that we can use. First things first, I have connected my sensor in a way that we have 3 cables, and the signal is the white one, the positive one is the red one, and the negative one is the black one. So I'm going to use this same pinout in the board to do the same connection. So I'm going to start with the black one, which is going to be here in pin number 2, the red one, which is going to be in pin number 3, and I'm going to skip 6, 1, 2, 3, and this is where our GPI 0 goes. And that's it. That's all we need to do. Let me try to see if I can focus this better so you can see the results. We're going to perform this task in a new function that we will use to spawn a thread. So we're going to define the function here, and I'm going to create it here. And this is the function that we will be using for reading the noise level. What we want to do here, when we were accessing the peripherals, we're going to define the ADC, the analog to digital converter. So there are a couple in the board, and we're going to be using ADC1. Also, we will be using the pin
that is connected to the sensor, the one with the white cable that I showed you before. So we're going to have that accessed also here. With two things in place, we need to modify the signature of this function so it supports ADC and the ADC pin that we are using. So here we're going to have the curly braces, so here, and this is where we are going to put the code that we need for reading. We take these two parameters and notice that here I'm going to create what we will actually be using for reading the values. Initially, we wrap a driver around the ADC and we provide a default configuration. Then we provide a driver around the channel pin that we have provided. And notice that this structure has a generic parameter that is a constant. This is the attenuation level, and it is initially set to dB 11, so 11 decibels, which will make our sensor very sensitive, and we can always change it later. We can use known or dB 0.5, I believe, and there is another value. Initially, I think that this value should be good enough, and if we have any issues later on, we can change it. The thing that we have to do here is to import all the variables that we are using. So we want to import the ADC pin. We should also import ADC1 and the ADC driver, which will be this one. And not only that, but also the ADC and the ADC channel driver, which is this one, and the attenuations. So now that everything seems to be fine, other than complaining because we are not in an endless loop in this function, we are ready to move on and read from this ADC. So we add a loop, and within the loop, we're going to initially wait and read from the ADC using the ADC channel that we had. This should be, let's make it consistent. So channel, we need the DRV. And we should be reading from the pin and obtaining a value. We are going to print the value and show it in the console. And we also need to be able to spawn the thread that we are using here. Let's go here and spawn this thread with the ADC, the analog to digital converter, and the corresponding pin. That should be it. Let's move to the terminal and let's try to run this. Ergo R. So we send the firmware to the board, and right after, let's stop it here, we don't need more values. Right after this execution, we get some values. These are basically background noise. And let me run it again so you see that it does some work when I get close to the device. So let's use cargo R, run it. And here, if there are more values here when I get close to the mic, yeah, that should be it. That is so good. We are able to measure sound from the microphone at a very low sampling rate, I reckon, but still we are getting 100 samples per second. Yeah. The thing is that we are going to transform these samples into noise data. So we're going to compute the root mean square of a buffer of 5 samples in order to transform those sounds levels into decibels. Not exactly how this is done, but we're going to use 5 samples in a buffer, and then we will be rotating that buffer. So we will be getting 5 samples, decibels, 5 samples, decibels, and so on. So we will use the computing capabilities of the ESP32 here in order to transform the data as it comes from the mic into decibels, or roughly decibels. Let's create the buffer that we're going to use for putting the examples. So here I'm going to define the size of the buffer and instantiate the buffer. This is going to be constant. We are going to be a sample up to 5 and then coming back to the beginning and doing the same over and over again. In this case, we have created the buffer to hold 5 samples. And here we're going to put a for loop for each one of these samples. And inside of the for loop, we are going to do the same kind of measurement that we were doing before. Let me move this a little bit up. Let's put the cursor here. And what we're going to do here is wait for the 10 milliseconds as we were doing before. And the main difference is that now we're reading the value. If we get any error, we will basically put a 0 in the buffer in that position. Otherwise, we will put the value that we got from the sample. So we're dealing with errors by having a 0 added to the buffer. Now that we have done that, we can use a variable here that we will use to compute the root mean square. And we're going to define it at the beginning of the for loop. So after we start a for loop, we create this variable and we're going to use it to compute the addition of each value here. So we don't need to do it here because if it is 0, the square value of 0 is 0 and adding it to sum doesn't change the value. So we're only doing it when it has some value. And this sum is going to hold the summation of squares, the summatory of squares. And this is what we're going to use later to have this value printed. And this will be here. Let me format this one. So we're going to calculate the decibels as 20 multiplied by the summatory divided by 5, the length of the buffer, and doing the root square and the logarithm to transform into decibels. And then we're printing the buffer, the sum, and the decibels, just to verify that everything is done correctly. We're going to remove the code that we were using before, and we are going to go back to the terminal. Let's go to the terminal, and CargoR should be able to do that. I'm getting that close to me. I flash the firmware, and now I can change the values. Okay, that sounds good.
What we have done so far? There are still things that are pending that we haven't solved yet. But in this episode, we have created the initial version of the firmware, and we are able to read data from the sensor and also report to the user the status of the device. Not only that, this data is coming from mic, and we're transforming the data from the mic into some measurement of noise. Not exactly in decibels, but something similar to that. That's good enough for us. In the next episode, we will be modifying the firmware that we have written in order to use the Wi-Fi. We will connect to the Wi-Fi, and then we will send the measurements that we have done through MQTT, the MQTT broker. The data is going to be stored there, collected there in the collecting station, and then we will use it to upload it to LS and use it from there with time series. Get ready. Meanwhile, stay curious, hack your code. See you next time.